everyone, welcome back to EE360. So for today, let's put this down. For today's lecture, we will be implementing difference equations. So we're actually going to go over something practical today. So we're going to go over the assignment. Right, here's our computer assignment 2, which is located, if I wanted to show you more practically. Aha, here's my little web page, which is located on Dr. Baker's website. Click here, click on courses, 360, look at that. Homework assignments, all the lectures, all the PDFs, all the quizzes. Homework assignments, computer assignment 2. All right, and now we're back to the assignment. So just in case someone is asking, hey, where do I find this material? Right there, which I've also been sending a whole bunch of announcements. Implementing difference equations. So we're going to start doing some practical stuff. We're going to see some cool stuff, and I'll be showing you how to implement this in MATLAB. So we're going to go step by step. So for those who are who are kind of scared of MATLAB, don't worry, I'll help you. So if you go over this introduction, it'll show you how to make statements. So if you wanted to know how to implement a for loop, it gives you a for example, and then it tells you, it generates a signal. If you don't believe me, just copy this. Let's go to MATLAB. Oh, look, remember this was the previous assignment, previous thing that we went over in the last video, lecture 4, which was this. So let me just declare that. Actually, let me show you this. If you ran this, there you go. Actually, CLC, clear. There you go. Let me run that again. If you ran this piece of code, you get n is equal to -2 to 2. And why do I have that there? And then you're probably asking, what is this? N plus 3. So actually, before I talk about, let's talk about that. So in MATLAB, matrices are all implemented where if I had x of something, it's gonna give me a matrix like A, B, C. So just 3 positions. So position 1, 2, 3. So that means if I put in a 1, then I'll be calling in 1, then 2, and then 3. Really simple, right? If this is 0 or anything that's negative, you can't actually access this vector. You can only access, the first element is 1, element 2, element t, position 1, 2, 3. So when it's asking, let's see, for n is equal to -2 to 2, this right here just declares n is equal to -2, -1, 0, -1, -2, right? So here's position 1, 2, 3, 4, 5. 5 elements. And then x of n. So how do we make this one 1? We want this one to be 1. So your objective is to make this 1. Okay, so if we're here at -2, here's -2, we punch this into here. How do we make this 1? -2, well, you just put a +3. And then if you put -2 plus 3, and you get 1, which is our little happy thing, which is equal to n. And what is n equal to? -2. And then you start going down the road. So that's like the simplest way I can explain for loops for you. So let me show you what I have right here. So yeah, if you go through this, it's really nice. It tells you what to do. It's really simple. Here's your first experience into what a difference equation is. So in the last video, we went over differential equations. That's my error. So the analog version of the linear systems are differentials. So just d of something over d of t. Let me write that down. Separate piece of paper. So in the last video, and it's my mistake, I'm learning. So analog, we have y of dot plus y is equal to x, right? Where this dot y is equal to dy dt. And these are differential equations. And then in the digital equation, the digital version is a difference. Which is basically, well, now we have to deal with differences. So here's y of n. It's the first thing we deal with. Plus y of n minus 1, which is equal to x of n. So now we have these like, oh, we have n minus 1. So for every MATLAB assignment from here on out, we have a digital computer. And since MATLAB is based on matrices and you have these blocks, we're going to be dealing with a bunch of these difference equations. So everything is discrete. So what I'm trying to say is you're going to be seeing this all the time, 3060, 361, 480 and above. So what we're going to be implementing in MATLAB is this. So hopefully, to make this video short, and if you probably wondered why am I a little tired, let me click that out. What time is it? Yep, I love producing content for you guys. To make sure you guys are learning, make sure, because there's probably one student right there saying, oh my gosh, MATLAB's so scary. Don't worry, I'll help you. We'll go over the actual assignment. We'll go over solutions too, to make sure you guys are all paying attention, or if you guys needed some more help. So remember the last time I was talking about block diagrams? So the direct form 1 block diagram is basically a feed forward into a feed back, right? And it was really, it's direct. It just flows, just goes straight forward. Whereas the direct form 2 block, the weird thing about this one was it had a feed back and then a feed forward circuit. And then this one just saved money and layout. Okay, but what if we wanted the best of both worlds? We had a transpose direct form 2, which is some weird block where it has feed forwards and plus feedbacks. It's a pretty cool, this is also known as canonical. And this is what they do, and this has both the best worlds of this and this, all in one package. So if you wanted to see what these were, just go to the previous video for more information on that. But for now, we're gonna go over this one. This is the one I want to do for today. And this is the hardest one. If you saw how I was drawing it last time, this one's the easiest to draw. Actually, no, this is the easiest because it's canonical. And this one's direct, it's also easy, but this one's the tough one. We're gonna go over the tough one, and then you can work backwards with how to implement these two systems. I'll let you do that as homework, and if you wanted to, the solutions are in the book. Please read the book, and we'll go over one solution. So, kiddokies, let's go over the direct form 2 block digital. Okay, and here's your solution of the day. So what is your assignment asking for? Let's look at it. You can look through that. Pretty cool, simple. I recommend just looking at that. Oh wow. And let's see. Okay, so we drew all these topologies in the previous video, lecture 4. So if you wanted to look at those answers, be my guest. or in the book. Read the book too. But we're going to go over a direct form 2 block. Then here's your big difference equation, pretty big. And we're going to try and draw this, and I'll show you how it's going to go. So we have y of n minus 1, and then y of n minus 2, minus 3. And then you have this x of n minus 1, 2, and 3, right? So what we're going to do for today is, how many delays do we have? If you look at this second part right here, it tells you, okay, indicate the number of delays. So, let's try it. So we have a minus 1 here, a minus 2 there, and a minus 3. So how many do you think we have? 3. Okay, let's start drawing. So we need 3 delays to generate that minus 3. So remember how we drew the direct form 2 block, and this is the hardest one. This is the one that I had a hard time trying to draw. You first draw your wire, but you remember that it's the feedback things, it's the feedback paths that come in, and a whole bunch of water has to add into itself, so you put this plus sign. Then let's see, you draw this arrow, and then we need to process it. So let's put a node there, and let's process it. And then let's use the letter D. This is your delay. Okay, and then let's draw a node there. And then this is our first feedback, A of 1. Plus sign. Don't forget to draw your arrows. And this actually here is A of 0, which is equal to 1, which is a wire. There you go. Don't forget that. Then let's draw D. Arrows. Node A of 2, and then D. There we go. There we go. And that right here is your feedback path. You understand? If you look at the previous video, you can say, what we did was, we had the feedback and then we had the feed forwards. You could redraw these delays, but if you look at the technique that we looked at in the previous video, the direct form 2 block diagram, we save a lot of money because we reused the delays. So reusing these delays, and if you look at the assignment, here's our 3 delays, and here's our other 3 delays. So now let's draw that. So let's draw it right here. Here's our first block, B of 0, and then this adds here, and here's the output. Yay! B of 1, plus sign, and now let's share this piece. B of 2, plus, and B of 3. Draw that node. And there you go, and here's your feed forward path. And there you go. That's how you draw the direct form 2 block for your assignment. But we're not done yet. So you're looking at this block diagram and you're saying, how do we implement it? Well, this is where we start labeling some stuff. So let's look at this wire right here. We dump some water here. Let's bring out running man. And we start running, right? We start going from here to here. Okay, what's the first thing we touch? It's this wire. We don't go through here, we go through this wire. Let's call this wire Q. Okay, Q of n. And now this Q of n goes through this delay and also goes through here. If I were to throw this Q of n into this delay, what's the output? Trivial? And now this Q of n minus 1 goes through these gain blocks back up here, and it goes through this other delay. What's the node value right here? What's this node if Q of n minus 1 goes through this delay? Q n minus 2. Hey, pretty cool. And then you start seeing the pattern. Q of n minus 2 going through the delay. Q n minus 3. Makes sense? In the a future video, I'm going to make this video short so you guys can just digest this video and have some fun. Hopefully it's 30 minutes. We're going to call these nodes like actual names, but for now, let's keep it in this topology. So we only have 3 variables to play. X, this middle internal node, and this output signal. Remember the definitions of it. What's the definition of an input signal? Output signal, internal signal. They might be in your exam. Memorize that. So now, here's our output y of n. What is it equal to? Y of n is equal to, well, we have this gain block, b of 0, but what's it being multiplied by? Q of n. Okay? Now plus, so this goes in here, plus what comes in here? Q, no, not Q. B of 1, Q of n minus 1. Q of n minus 1 times B1 gets in here, plus. Now you start seeing the pattern, B2, B2, Q of n minus 2, plus B3, Q of n minus 3. And there you go. Use the purple marker. Or that's pink, I guess. That's your first solution. But we're not done yet. What is Q? Can you tell me what Q is? No. Don't worry, we'll solve for that. Here's Q. What is Q equal to? So let's look at where it's coming from. It's coming from this adder, which is equal to an input. Q of n, oh, I like this marker, is equal to the input, the current input, plus, what are we taking in? This a of 1. What's this a of 1 coming from? A q n minus 1. Okay, plus, we're taking this a of 2, and now you start seeing the pattern. And then plus, a of 3, q n minus 3. And there you go. Let's box this in. And yes, please derive the equations. These will help you with the assignment. The rec form 1, 2, and the transpose rec form 2. So it can help you program. And I'm trying to do this hard one because this is the hardest kind of to program. And I'm about to show you something right now. So how do you implement these equations? So the first thing you gotta ask is, okay, if we're writing code, which line goes first? Do we write this line, the output, or do we write this internal signal? So let's look at Running Man. Here's Running Man. He's just running around. What's the first thing he touches? What's the first node he enters? Here he is. He's in node 1 right here, the input. And he goes here, which is Q of n. So he's right here running around doing whatever he wants. And then what's the next node he goes into? The output. And then this other internal stuff. So the first thing you should implement is this Q of n. And then the next thing you should implement is the output. So this is page. Gotta write my numbers. This is 2. This is 3. There you go. How are we doing on time? 20 minutes? All right. Let's see if I can finish this in 10 more minutes. So we're going to implement a for loop right now. So if you were to type this into MATLAB, one thing I got to mention to you is, let's look at this. So it's asking us to calculate the system's first 51 outputs. So what that basically means is we have a time scale that's 51 length. So what we're going to have to do is declare time n is equal to 0 to 50. Why didn't I not put 51? Because this 0 is also a number. If you typed in length of n, you're going to get 51. Don't believe me? Don't trust me? Let's see. N is equal to 0, 51. Wait. There we go. And then length of n. Wait, 52. What did I type? Typed in 51. It's late. It's almost midnight. But I love making videos for you guys to hopefully it's helpful. I don't know if they're helpful. If they are, just let me know. 0 to 50, and then length of n. 51. There we go. I was having a weird panic attack. Believe me? So now, here's the part where people start getting confused and scared and lost. We have a delay. We have a delay right here, right? What happens when, let's look at this, n minus 3. What happens, or n minus 3. Actually, instead of calling this n, actually that's our time. For I is equal to 0 to 50, right? What happens if we do something around here, I minus 3? If we put the 0 here, here's the array. This is an array, by the way, an array. If we punch in the 0 here, then we're going to get x of minus 3, which crashes MATLAB. It's not what we want. So there's two methods you can play. The first method is, okay, let's just fix this. But I don't recommend it. So what I'm trying to say is, you can make this term go to 1. So you can do x of I. So let me show you. If you had, for example, how do I do this without making it too long? Instead of doing this, q of I, not q of I minus 2 plus q of I minus 3, right? Instead of, like, we're gonna play with this. We're gonna, if you wanted to, I highly do not recommend it. You can try to make this force this to 1, where you make this one q of I, but then how many numbers, what did we add to this? We added 3. So that means this also gets added by 3. I plus 2. 2 minus 1 is 1, sorry. Which is equal to q of I plus 3. You can do this. You can do this. But this is the controls way. And controls people don't like negatives. They like positives. They like looking at these numbers. You could do this, but I don't like this. I'm a DSP engineer. I like digital signal processing. We're going to call this option 1. Okay, but I'm going to show you option 2. This is page 4. Option 2. Where we have the for loop. I is equal to 0 and 50. There we go. And we just write the equation I. Just keep this I, and then let's do q of I minus 2, and then plus q of I minus 3. So we have this, but if we punch in this here, it's gonna make this blow up. So instead of messing with the equations, why don't we just mess with the actual for loop itself? So what number should we put here, the first number, so that this doesn't break? So if we put 4 in here, plus 4. If you put a 4 in here, that means 4 minus 3 gives you 1. And now your thing works. Actually, yes, it does work. Actually, yes, 4. This is 4 minus 3 gives you 1. So Q of 1, which is the first array. Okay? But what we do here on the left side, we have to do on the right side. Okay? Now the next thing I got to tell you is we have delays, right? We have n is equal to minus 0. What's before that? No, nothing exists. We have from n is equal to 0 to 50. We don't have an n is equal to minus 1, minus 2, minus 3. So what you're going to have to do is, okay, so if we had, let's call this one 1 for now. Q of n I minus 1, right? We have something before n is equal to minus 1, right? How do we fix that? Just change it, minus 1. And now we dealing with the worst case. How do we deal with this? You have this minus 3. Just change it to minus 3. Okay. So that right here is how many delays we have. So here we have a minus 3. Here we have a minus 3. We're dealing with the worst case, so we just put the worst case right there. And then here's our 50 right there. So one thing I kind of want to talk to you all is, you see how this is a minus 3 and here's a minus 3. What happens if this is a minus 5? Then this is also a minus 5. But then what about this? This also changes too. All right, so I want to show you a pattern. So let's call this a variable. I'm going to call it, eventually, I'm going to call it pre-length. This is something, this is due to the effects of the delay. If you see a pattern, here's a 3, here's a 3. Okay, let's just declare a variable, just reuse one variable for 2 spots. Pre-length, right? And then eventually, okay, what if Dr. Stewart asks, oh, I want 100 or 200. Let's call this one an end length. Okay. So now you can use this variable and change it wherever you want. All right. So you can use it right here, etc. So now instead of this plus 4, what I'm trying to get to you is this plus 4 can equal pre-length plus 1. Why the plus 1? Because, well, MATLAB doesn't like 0. We have to put the plus 1. It's inevitable. You have to. So that's what I want to get to y'all. All right. Let's start coding. So what I've done for you guys is, okay, here's lecture 5, and I'll post this the code online. So remember what we did last time? I'll run the solution. Here's the solution to number 1. This is how you draw it. Make sure you write the equations. So here's x of n, c of n, y of n. Determine c of n. Just b of 1. Oh, b of 0, b of 1. Okay. Determine y of n, but you have to use c of n. Do not use x of n. So you have to have 2 lines of code. I'm looking for 2 lines of code. Hint, hint. The output and c of n. Define them. Which one's the first one you define? Wherever the running man goes. Second one. Okay? Easy. So we just went over the code solution like that. So really, really simple. But we're doing the hard one first. You can look at the previous video for the solution to that. So I've already written some code down. We're going to develop some programs. First things first, clear variables, because it's nice to have a clean thing. I defined a variable pre-length. So this is our how many spaces behind n is equal to 0. So knowing that we have 3 delays, we have 3 zeros. So I put that there, and then our end length. So just in case Dr. Stewart asks, like, okay, this and this changes, you can easily do this at the beginning of your code. And now I have my time. Here's the beginning of time. Here's the end of time, and then I just create one big time. I put this minus 1 there just for fun. The negative time, the positive time. Now we have a big time. And then here are all the variables, which, okay, if you wanted to, here's a shortcut way. This is stuff I'll show you later. Here's the assignment. Do this. Copy. And I literally had to retype this to do the following. And don't forget your semicolons. Sweet. And now let's look at the second surprise I have. We're gonna do, second example, a Kronecker delta. So remember how a Kronecker delta works? I'll show you. So look at our variables. So the delta function, so we just changed the time, right? Here we have -3 to 50, right? So now we have to start at -3, -2, -1, here's 0. Here you have this delta that just goes to 1. So here's 1, 2, 3. Now you see why I have this pre-length right here, which is a positive number. Make sure it's positive. And then you can do 1, 2, 50, which is our end length. Okay, simple. So now I'm going to show you how to write this in code. So right here I have zeros. Here's our input. How many zeros do we have before n is equal to 0? Our pre-length, which is equal to 3. Right? 3. And then here's our big fat 1. Okay, if you wanted to, you can put the commas there if you're OCPD. And then here's our big 1. And then how many zeros do we have from, well, n is equal to 1 to 50? The end length. Now you see why I declared those variables? Makes life simple. And then what I want everyone to do right now is start pre-allocating memory. Just allocate memory. So MATLAB, you can dynamically create memory by just doing like, oh, come on, is equal to 1 plus 2 or 3. This is how you just dynamically allocate it. Just automatically does it for you. But in reality, you should be doing like a is equal to 0. Just pre-allocate memory. Like, oh, declaring variable integer or something like that, right? And then to declare a vector, this is how you would declare an empty vector. So that's how I would show you right there. Simple. So why did I do this? Length of n. You know that this is your time from -3 to 50. How many elements do we have from here? Well, from 0 to 50 is 51. And then we have 3 zeros, 54. And then we know that our input should also be 54. So that means all you got to do is just play with the time. The length of n itself, the length of the time. And there you go, really simple. And you should do the same thing with the queues. And now let's start writing the block diagram. So what I did here is a little different than what you could be doing. Let me just write some spaces to show what I was doing. So there's two ways of doing this. I did it this way because this is my natural way of doing it. I kind of like using one variable instead of creating a bunch of memory. So you can either do this way, or okay, let's follow the procedures. Pre-length plus 1, all right? And then here's another thing. If you looked at our code, you see this plus 4 right here? This plus 4 is this. So this is also here too, so connect the dots. Yeah, you see? Pretty cool, huh? So whatever you do in the beginning, you have to copy it right here. Let's paste that right there. And then that right there is just our end time, so 50. So we're actually going from value section. Oh, that's because I did not. Let me just run all that. F9. And now we have that in memory. Did we clear variables? Yes, we did. Let's run this F9. We have 4 to 54 because of that plus 4. There you go. It makes sense. So you can do it this way, which is the way I'm trying to teach you right now, or you can play around with this if you know how to extract variables. So now that we have that, I drew it the DSP way, which was, let me show you the DSP way. Oh, let me write that down right here. Which is this. This is the DSP way. Engineering. So this right here is DSP engineering, where you just keep the actual delays. You have minuses. See this minus, but then you change your time. So that's how you get away from this loophole. So now you have your nice difference equations, which have negative times, this minus right there. Whereas the controls way, they put pluses in there. You can do that, but it's hard. But the positive about this is that you can keep the same time. You don't have to play with the time. So you can either, choose your poison. But I think the DSP, like, you just look at this, it looks nice. This might look a little weird, but if you know how to control it, you can. So, and there you go. And then here you just literally type in your Q of n, the first line. Here's your internal node, which is taking in the input. I'll show you that right here. Where is our equations? Found it. So first node, we just take our input n, and then there you go. A of 1, Q of n minus 1, A2, N2, A3, and you see, simple. Just copy and have some fun. X of I, A of 1 dot times, don't forget the dot, because these should be points, but you never know. And then one row, and then here's the column we're trying to access, and just copy it, and don't forget that semicolon. And then we just do the same thing with the output. So here's the internal node, and then here's the output, which has a similar format. Instead of this one has A's, but this one has B's, and this one doesn't have the input. You see, there's no input here. This is just purely internal nodes, whereas this one does have an input. So do be aware of that. And here it is. And there you go. This right here is your direct form 2 block diagram. So congratulations, you have successfully finished this little code. And the other block diagrams, the first block diagram has 2 equations. The third, the transpose direct form 2, I think it should have 2 equations as well, but I could be wrong on that. Double check on that with me. But this is how you would implement it. And now, if you ran it, no errors. So everyone now has a direct form 2 block diagram done. Do you understand this? Do you understand what's going on? Here's your internal node. We're writing it the DSP way. Like, look. Just ignore these ones. Look, here you have an I minus 1, I minus 2, I minus 3. Let's look at the assignment. Oh, look at that. We have it's not I's, it's N. Here's an N minus 1, N minus 2. This is DSP engineering. The controls way is weird. This is a plus, and this is actually K plus 1, K plus 2. I don't like that. Too weird. But this is simple. The only thing that changes is you have to play with this. It's just a game. It's just, you gotta play around with, oh gosh, like, it's just crazy. Actually, instead of n, you can do end length. See? You understand what's going on? What is this? This right here is how many delays or how many zeros we had before n is equal to 0. And this is our end length. How many zeros do we have after that? And then now you're asking, okay, what do I do now? So using STEM, here it is, STEM, title, and subplot functions. Oh, subplot, I'll talk about that today. And then for part D, explain in your own words what is happening. I'll do that too. That's very important. Figure, I don't know, 6, 9. subplot. Should we do subplot? Yeah, you'll do subplot on your own. 1, 2, 1, 3, 1. Stem y. Note the time n y. And okay, let's make this one R. Someone was asking me, should I do just R or should I do this? The reason why I do this is because there's a function called plot, but we're not going to use that. But like the reason why I do this is because plot gives you weird stuff, but don't worry about it. This or that, this is acceptable. Go ahead. Line width 3. There we go. Title DF2 DF2 or Kronecker delta. And actually, let's do my cool trick thingy. There we go. Direct form 2. Actually, ooh, that might be weird. And we'll figure it out. Oh, that's not good. Oh, cuz. So subplot, it basically declares here's your rows, here's your columns, position 1, position 2, position 3. Okay, I'll show you. Here's position 2. Ooh, like that? Actually, let's get rid of that. Plus 3. See? Puts it on here. It divides 1 row, 3 columns. So here's the second column. Pretty cool, huh? But I don't want that. I want to do this. 3 by 1. And let's put that in 1. There you go. And then now you have your Dirac delta or Kronecker delta. Actually, let's see. Plot the inputs and the outputs. Okay, so you're going to plot your input and direct form 1, 2, and transpose direct form 2. So I should explain that. 1, 2, 3, 4, 5. So for your assignment, please. And oh, this is my last piece of paper. Huh. That is my last piece of paper. Okay. So this is 6. I have to rewrite this. So for your assignment, and oh my goodness, we're already almost over 40 minutes. It's asking plot the inputs and the outputs. So what you're gonna do is here's your thingy, and I don't know what's the best way of doing it. You could do a 4 by, so 4 rows, 1, 2, 3, 4 by 1. So 1 column. And then you can generate your input X. Blue. So X is going to be on this one. Here's X, which is literally your Dirac delta. Dirac delta. Kronecker delta. And I'm going to give you the answer right now. The answer to A is this. This. It's literally this. This is your answer. For all 3 block diagrams. Because, look at this equation right here. Look at this output. If you solve for this output, what's it going to equal? It's going to equal this figure. So, how to tell you if you're doing this right? If all your block diagrams look the same. Or not block diagrams. So the answer to this, the equations, so whatever you developed here, and this, and this. All three of these systems have three different equations. Three different sets of equations is what I meant to say. However, they all equal the same output, which is this right here. So you're going to see, okay, I'm going to probably BS, or not BS it, but cheese it. I'm going to cheese it. Yeah, let's cheese it. Okay. Let me show you this. 2, 3, 4. You're going to like this. Oh, wait. Ooh. I don't know if this is gonna work. And then I don't know if this is gonna work. So here's 1, here's 2, here's 3, here's 4. This right here is our, I'm not gonna title it this. That's the reason why I was doing it. Direct form 1. Oh, I did have it. I don't like this. There we go. Copy 4. I didn't copy the space. No, copy the space. There you go. And erase that. Erase that. Oh my gosh. What time is it? Yep, it's 2:22. Wait, no. 2:22. 12:22. 2, 3, 4. This right here, the first thing should be the input X. And let's color it, red, which is the Kronecker delta. Money sign, delta of n, money sign. Interpreter text. And this one should ideally be DF1, DF2. I'm cheesing this right now, so don't do this. You better have different equations. This right here, it should be Y1, 2, and 3. Or DF1, DFI, DF2. You know what I mean, right? Okay. TDFII. There we go. And I don't like that. I'm going to color this blue. Color this magenta. Don't use yellow. I don't like yellow. You can't see that. Let's show you how, like this you can't see, it's hard to see, so let's just use black. There you go. This is ideally what you should see. This is the impulse response, which is a key word for later. You kick your box, and what does it do? What does this system do? You throw water into here. Splash. Okay, water just goes in here and just. And how long does it take to get out? Let's look at that. Actually, no, not that one. So here's 1. You kick the box here. 1, 2, 3, 4, 5, 6, 7. After 8 iterations, and actually it starts bouncing. Ooh, that means there's some harmonics in there. It might be a little unstable. Yeah, there's a resonance, and that means you got a pull in there. We'll talk about that later. But this is ideally what it should look like. The direct form 1, 2, and transport direct form 2 should all look the same. If they're not the same, then you have a problem somewhere. So that's how you do problem A, but make sure you write your own equation. This one has its own set. This one has its own set. Check the book for your answers, and let's see. Let's go over that last one. Actually, I can't show you that. I have to get this done. So, in reality, this system is a filter. I'll tell you right now, it's a low pass filter. So what happens when you take this slow signal and this fast signal, you see this one right here is a slow signal, here's a fast signal, and you put it through this filter, this system, you're gonna get this right here gets filtered out. This fast signal gets filtered out. So that's what you should see. If you add these together, you're gonna see some crazy mismatch. But this system right here should filter out that. So that's your answer for that. For part D, explain in your own words what's happening to the input and the output. I already told you. And now we're going to use the filter function. What's that? So I will tell you what's going on with this one. I don't know what's going on. What do I do? Don't worry. Help filter. And now you figured, you see it, MATLAB is supposed to be super helpful. Let's see what it's asking for. Filter, B-A-X. It takes in vector X, your input, and then it's whatever your system is. Here's the B's, here's the A's, and it creates a filter. So instead of building this, yes, you can build this in your program, your Arduinos, whatever you want. Instead of doing all this math, go for this. Use your gains, use your op amps. X size 3. Implementing the filter function. Exercise 3A. So if I were you, B is equal to, B is 0, because I'm lazy. Oh. I'm tired and sleepy. 1, 2, 3. Oh. There we go. And then this is a 1. Actually, okay, A0, A1, A2, 3. And there you go, because look at this. You have A0, B0, A1. See that? Here, see the pattern? That's not the pattern. See? A0, A1, B2, B3. We just put them in vectors. Our B terms, our A terms, LOL. And now, Y filter or something like that, which is equal to filter B, A, and then X. But we have to reinstantiate this X. Suppose this is X1. Make sure this is X1. I'm going to change that. X1. Let me run that again. Okay, runs. Let's call this one X. I don't know. Actually, someone's going to get mad. LOL. Where? I'm doing these weird variables because you have to try to keep instantiating new variables, or if you know what's going on, you probably know what to do. But for those who want to have, because there's 4 inputs, please do not mix up your X's and your N's and everything else. You're gonna be sad. Like, you run this code, you run the Dirac delta, Kronecker delta when you meant to run the cosine, so make sure to keep instantiating stuff. Remember, this is our Kronecker delta, 0s, 1, and 0s. And there you go. And figure stem N and YF. I don't know if that's going to work. title using the filter function. And then to lazy. There you go. There you go. And is that it? Subplot functions. Plot the inputs and the outputs. So 8 plots on 4 pages. So that means 2 plots. Oh, I know what's going on. Subplot. 2 rows, 1 column. I'm going to put this in position 2 to be different. And then where's the input? Here it is. So you don't actually have to put this there, because this takes care of it. So 2, 1, 1. And yes, you can write it that way. LOL. Boom. And now you see this curve, and actually I don't like that curve. I'm gonna color it. Here we go. Yay. Fat. Oh, I forgot one word. Filled. And you guys can type that in. There you go. Filled. How do you tell if you have the right answer? Here's your first equation. Here's figure 444. It's figure 69. Let's run the whole thing. Here's our Kronecker delta. 1, 2, 3. Here's that 0. 1, 2, 3. Look at that. They're the same. It ends at 50. Yay. And oh, something's not right. This is the right answer. This is not right. I did something wrong. That's no bueno. It's no bueno at all. What did I do wrong? X of 1. Take this input. A of 1. Q, Q, Q. B of 0. B of 1. 2, 3. A of 1, A of 2, A of 3. B of 0, B of 1, B of 2, B of 3. Run that. That gives me that. Something's not right. I really hope it's not this. Nope. That definitely doesn't look right. There we go. Here's the input. We're taking an input. Let me check my notes. That's not right. There we go. A of 0. Unless I have a minus sign. I shouldn't be having a minus sign. Let me check some quick old notes that I have to verify that everything's going on pretty good. We're already at the hour mark. I hope we don't go overboard. Check something. Image 1. Check something. Don't worry. I'll take care of y'all. Let's see. Interact form 2. I have minus signs. I made the biggest mistake. So there's one thing about difference equations, and I need to explain it to you right now. So I should be tackling the actual difference equation itself. Let's plot the assignment. See this? Let's solve for y. y of 0, actually, a of 0, y of 0, y of n, plus a of 1, y of n minus 1, plus a of 2, y of n minus 2, plus a of 3, y of n minus 3 is equal to b of 0, x of n, plus b of 1, x of n minus 1, plus b of 2, x of n minus 2, plus b of 3, x of n minus 3. Solve for y. What is y equal to? Y is equal to, let's do our feedback paths. B of 0. Okay. There we go. So it just stays the same. Here's a feed forward path. Plus, we need to move this term to the other side. So minus a of 1, y of n minus 1, minus a of 2, y of n minus 2, minus a of 3, y of n minus 3. And then what happened to this? Ideally, you divide the entire thing by a of 0, which is always equal to 1. So the point is, I forgot some minuses in my feedback. So all these a terms. And then I look at this and then I ask, how do I make this a minus? And let me think. I have one solution. Just put the minus sign in there. Or I think what they do is because you ideally would wish these were just A's, like just punch in your A's, because that's what they should be. But you can also put them there, the minus in there if you wanted to. But point is, in a feedback system, to make a feedback system work, you need to have negative feedback. So that means the minus has to be right here. Or actually not that, it has to be minus right here. There you go, I found it. You have a minus that goes through here. You remember your op amp. Here's your plus. And then here's your resistor. I'm just going to draw something like that. It feeds back into the minus terminal, and here's the plus. I kept drawing the plus there, but it should be a minus. All op amps have a minus sign there. So if you were to redo this, minus, minus, minus. Grr, we just wasted all that time. It's okay, don't worry. Easy fix. Minus, minus, minus. Run. There you go. The reason why we use the filter function in the first place, here's the filter function. Using the filter function. There we go. Now let's put this on the side. Put this on the side. Click on this top peak. Look at that. They're the same numbers. Let's look at 10. It's like a 10. We're done. All right, so this should wrap up the first half of the assignment. And literally, if you just, okay, don't copy paste, but understand what's going on here. Obviously, this needs to be direct form 1 and transpose direct form 1. Find those equations. It's in the book. And yeah, this should be an easy assignment. And change your inputs. You know how to change your inputs. If you were to be smart, I'll show you this other thing. Exercise 3 C. Your input X is equal to X sine. I think is what it is. I don't know. Okay, don't be lazy, David. Cos. going to do this. Cosine. Actually, is it a unit step? Yes, it's a unit step. Copy this. No, wait, no, copy this. These are a pre-length, and then here's the first point. All you gotta do is, should you cosine of 0.05 dot times n, should you be doing that? No, don't do that. Just do this, 0.05 times pi dot times n. So that should give you 1 by 54, but you gotta zero the first terms. Here's your unit step, which you've created here. So, okay, I'm literally doing your assignment. Okay, you students are asking for it. Oh, you got it. And then you know how to do that once. Dot times unit step. You guys getting your money's worth? And then because I am lazy and I kind of have to go to sleep, x cos, the input cosine. There you go. That's your input for exercise 3C. Does that make any sense? All right, everyone. So this should be a good packed video. This should take care. And then look, note exercise 3's output should look like exercise 2. This is how you do the first half of the assignment. So have fun with it. Make sure you write your equations. And if you have any other questions, let me know. The next video, I will be talking about state space equations. So, all right, everyone. It's nice teaching y'all. See you guys early morning Wednesday. All right, take care.